Okay, so we had a great question from the studio audience, and that was, but sir, what if the object's heavier than an object? Won't it fall faster? And it definitely won't. Remind me in class tomorrow, cohort B, and we'll do the demonstration where we prove Galileo's point. And Galileo, remember, said that any significantly heavy object, negating out air resistance, will have a distance formula of, when it's free falling, of 16t squared. And that doesn't matter if it's a crumped up tennis ball or if it's a 50-pound weight. They will still have the same distance formula when allowed to free fall in air. But we will talk about this. Galileo, Galileo, Galileo Figaro. Anyway, let's go. So examples. Find S of 1. So we know what that means now, right? That means the instantaneous speed when t equals 1. We're going to ignore units. For an object with a distance formula given by d of t equals 3t plus 5. So that's a different distance formula. This is not an object falling freely in air. Otherwise, Galileo would come and yell at us. It's a different distance formula. And they would like to know the instantaneous, and we know that because that was by definition up above. We said that whenever we have S of A, that's going to represent instantaneous speed. So the definition is going to be that the instantaneous speed at 1 is going to be given by the limit as delta t approaches 0 of the distance formula of 1 plus delta t minus the distance over 1 of delta t. And we owe Newton for this. Newton's the guy that came up with this whole idea. He said, okay, we'll take the distance formula at 1 and we'll add a little bit. And then we'll subtract the distance at 1. And that will be my delta d. I hope you're understanding this. That's your delta d. And so he's got delta d over delta t, but it's not at 1 point anymore. When it was at 1 point, we got this. And that was a bad thing. So he said, no. I got it at 2 points. I'm going to have it at d at t equals 1, and I'm going to have it at the point t equals 1 plus delta t. Those are 2 points, and everybody agreed with him. His first point was 1, and his second point was 1 plus delta t. And then he went and played a fast one on them. He said, and I'm going to allow the limit as delta t approaches 0. So I'm going to allow it to get smaller and smaller and smaller and smaller and smaller and smaller and smaller forever, until eventually it's so close to the instantaneous rate of speed that we'll just take it as that. Because it's going to be, the difference is going to be so small nobody cares. So it's a little bit of a sleight of hand. So what we do here now is we do the limit as delta t approaches 0. Now it's 3t plus 5. So it's t1 plus delta t plus 5, subtract 3 times 1 plus 5 over top of delta t. So we got to be careful with our math, right? So we're taking the 1 plus delta t and we're plugging it in for the t value in the distance formula. So now we work this out. We work out the limit as delta t approaches 0 of 3 plus 3 delta t plus 5 minus, now 3 times 1 is 3 plus 5 is 8, so it's minus 8 over top of delta t. So this is going to be the limit as delta t approaches 0 of 8 minus 8, so it's 3 delta t over delta t, which is going to be, now if I take the limit right now, I'm going to get 0 over 0, aren't I? That's indeterminate. So we know better, right? We're going to reduce those, and we get a instantaneous rate of speed of 3. Huh, isn't that interesting? Now, if we think about that for a minute, my distance formula was 3t plus 5. That is a linear function. This has a y-intercept of 5, and it goes over 1 and up 3. So this is actually the linear function that looks like this. That's my distance formula, or my distance function, sorry. 3t plus 5. So when someone comes along and asks me for the rate of change at a particular point at 1, it's not surprising that we're talking about the instantaneous rate of change right at this point. And notice, since this is a line, the slope everywhere on this line is going to be equal to 3. We know that from grade 9. So in fact, our work with Newton is making a lot of sense with our work with grade 9. The slope, the instantaneous change at that point, is 3. And it says here that the rate of change is 3. And that's wonderful. Let's do another example. We could have. But we're not going to. Now let's do this one. Determine. Can you see? There we go. Determine S of 2, ignoring units, for an object with a distance function d of t equals t squared. Now again, that's not a free-falling object in the air, otherwise Galileo would come and yell at us. It's something else that has a different distance function. But if I want to know that it's instantaneous velocity when t equals 2, and I think I'm going to point this out one more time. This stands for instantaneous velocity when, or at, t equals 2. That's what that stands for, and we should know that. So we should know that the definition of instantaneous velocity is the limit as delta t approaches 0 of the distance of 2 plus delta t minus the distance at 2 over top of delta t. And again, what we have here is the limit as delta t approaches 0 of delta d over delta t. That's what we have here. So it's the limit as delta t approaches 0 of the average rate of change, or the difference quotient. I don't care how you think about it. Now this is the formula we need to be subbing everything into. So this is going to be the limit as delta t approaches 0 of 2 plus delta t squared minus 2 squared over top of delta t. Now that's unique for every different distance function, right? That always changes. So I hope you know how to expand these quickly. If you don't, you should learn. But anything of the term a plus b squared becomes a squared plus 2ab plus b squared. And you should learn that. And so this is going to become 4 plus 4 delta t plus delta t squared minus 4 over top of delta t. And if you're playing with little arrows and graphs and those lines, oh, this is going to be a harder question. And keep it out of my solution. Do it on another piece of paper somewhere. So what I have now is this 4 and this 4 are going to cancel each other out. I don't know if that's cancel. It's positive 4, subtract 4. And this is 4 delta t plus delta t squared over delta t. Notice if I allow delta t to approach 0 now, I'm going to get 0 over 0, which is indeterminate. You know better than that. So we're going to factor out a 0 term, and the 0 term is delta t. They reduce, and it leaves you with the limit as delta t approaches 0 of 4 plus delta t. Then we go and apply the limit. Ring-da-da-da-ding, ring-da-da-da-ding. We allow delta t to approach 0, and we get an answer of 4. And that was our second example. I'll stop the video there, and I'll be back in a minute.